Hello, geometers. This is Ms. Backfish, and I am talking to you today about density. And density in geometry very often has to do with area and volume. And sometimes you hear people talk about population density. You could talk about the density of an object. Something that is dense is going to weigh much more than something that's the same size that is not so dense. So that's one way of looking at it. Like a block of lead versus a block of styrofoam. It's like the molecules are packed much more tightly together. And that's the idea of density, is that how tightly packed together or not tightly packed together things are. That's a kind of an overview that applies to any kind of way we might describe density, is how closely packed together things are within that space. So two different ways we look at density, and really there are others in addition to this, but two of the main ways. One is in terms of, and this is maybe for like physical science and physics and that kind of thing, we talk about the mass of an object divided by its volume. So that's a standard density formula. We can go ahead and write that out maybe. Mass divided by volume. Population density would be the number of people divided by the area. Okay, so for instance, in a city, you would have a much higher population density than in the country. In the city, you might have, I don't know, 500 people living in 100 square yards. Well, that would be pretty tough, but cubic yards, that's a bad example. But basically, I don't want to give you a more specific example just because I'm kind of bobbling it here. But think about a skyscraper versus a street that has wide spaced out houses. You've got a much higher population density in a city where people are living, like maybe one person has 25 cubic meters to themselves as opposed to 25, I don't know about cubic miles, but something much larger. Things are just more spaced out outside of a city. So that's another way of thinking of density, how spaced out versus packed together things are. So this first example says the Verizon Wireless Amphitheater has approximately 100,000 square feet. Okay, now, square feet, we're not talking about volume. Square feet, we're talking about area. And here's why. People don't stand on top of each other at a concert. We don't stack people above one another. Everybody has to have some floor space. So we think about it just on a flat surface. So this is basically the floor space, 100,000 square feet. If the sold out Ed Sheeran concert has a population density of 0.12, there's a decimal there, assuming that all ticket holders are in attendance, how many tickets were sold? Okay, so this is a population density problem. So if the area is 100,000 square feet, my population density is the number of people divided by the area, and here my area is 100,000 square feet. Square anything is going to be area. The population density is 0.12. Then basically we have an equation with only one variable, only one thing left to solve for, and that's the number of people. So we've got 0.12 equals x over 100,000. If we have something in the denominator, the easiest way to get rid of it is to multiply by it on both sides. So I'm going to multiply by 100,000. And however many zeros you have when you're multiplying, that's how many places the decimal moves. So 1, 2, 3, 4, 5, decimal's going to move 5 places. That's going to be 12,000 equals x. So 12,000 tickets were sold. We have 12,000 ticket holders in the space, assuming everybody showed up. All right, so that one wasn't asking me the population density, it was giving me the population density, and I had to use this to work backwards. Next one. Some people believe that elementary age children carry school bags that are too heavy. They're proposing that school bags weigh no more than 20 kilograms and have a volume of 15,000 cubic centimeters. Jessica's father measures her bag. The base of her bag is 11 by 15 and the height is 26. So we're basically assuming the bag is a rectangular prism from the information they're giving me. Okay, the base is 11 by 15 and the height is 26. Does her school bag qualify if the density is 0.003 kilograms per cubic centimeter? Okay, so hang on one second. Let me think about this one. I'm not sure what they're saying here. Are they saying the density we're trying to achieve is that? So let's look at the calculator and come back up here and look at this. If school bags weigh less than 20 kilograms and have a volume of less than 15,000 cubic centimeters. Notice those are the same units we see here. And also, this can tell me how to set it up. Kilograms per cubic centimeter tells me to put kilograms on top of cubic centimeters. Okay, so according to this, they're proposing 20 kilograms per 15,000 cubic centimeters. So that would be in the calculator 20 divided by 15,000. All right, that's the density that they're proposing. So according to what they've told me here, I thought originally I was going to have to find the volume of this bag. But no, I don't have to find the volume because they're telling me this is the density of her bag. Okay, so it says, does her school bag qualify if the density is this? So this is the density of Jessica's bag. So I needed to take these to figure out what is the proposed limit on density. Density, let's call it a constraint. Like we want to stay within that amount. And that is 20 divided by 15,000 is 0.001. So if her density is 0.003, that's 3 times as much as it's supposed to be. That's bigger. So no, 0.003 is 3 times as dense as it should be. So that one was kind of worded a little bit odd. We had to think about what they meant by that. But this is a big clue. Anytime they tell me a density, the units tells me what I'm dividing. Okay. Next up, a construction company is preparing 10 acres of land for a new housing community. The land contains large rocks that need to be removed. A machine typically removes 10 rocks from 360 square feet of land. About how many rocks will need to be removed from 10 acres of land? So this is one, and this very often happens in density problems. We have to convert our units. One of the things, just let me point out about density problems, and it can be one of the most challenging things about them, is very often almost every one is a little bit different. We have to figure out what is the situation that they're asking me to figure out here. Okay, so this one we're going to have to figure out in order to use this information, that one machine removes 10 rocks from 360 square feet of land, I need to know how many square feet of land I have. All right, we have 10 acres. Okay, so if 1 acre, we have 10 acres, and each one is 43,560 square feet. That's going to give me well, I'm not really needing the calculator there. When you multiply by 10, it basically just moves your decimal over one place. So 600. That's a 6. Sorry, it's a weird one. Okay, so we have 435,600 square feet. Okay, if the machine takes 10 rocks out of every 360, I need to know how many times 360 goes into this to figure out how many rocks are going to come out of this amount of space. So 435,600 divided by 360. And we still have that number in here. And I get 1,210 rocks. Okay, so the density of water, this is another example I just wanted to do. Density of water is 1 gram per cubic centimeter. An object floats in water if its density is less than the water's density, and it sinks if the density is greater than the water's density. Will a toy in the shape of a rectangular prism that is 1 centimeter by 2 centimeters by 2 centimeters with a mass of 3 grams sink or float? Okay, so first thing I need to figure out is what this little toy looks like. 1 centimeter by 2 centimeters by 2 centimeters. It looks like this. Okay. So since we were told the mass, we know that we're going to be using this formula for density, the one that talks about mass versus volume. So I need to find the volume of the toy. So the volume is 2 by 2 by 1, which is 4. And I believe it was centimeters, so that would be cubic centimeters. All right, so going back to the problem. Will a toy in the shape of a rectangular prism with a mass of 3 grams sink or float? So, sorry, that's where I got that problem from. There we go. If the mass is 3 grams and the volume is 4 cubic centimeters, 3 over 4 is 0.75. And the units is grams per cubic centimeter. Okay, so this is my density of my toy, 0.75 grams per cubic centimeter. The density of water, and I've gotten back, I was trying to show just this problem, but you can see it right here. The density of water is 1 gram per cubic centimeter. 1 is bigger than this. So this is less than water. So that tells me it's going to float. If we have a density greater than water, we sink. If we have a density less than water, we float. Okay, one more problem I wanted to go over with you just because I think it's a really interesting problem. It says an aquarium manager drew a blueprint for a cylindrical fish tank. The tank has a vertical tube in the middle in which visitors can stand and view the fish. So you could stand in the middle of that. There's empty space there. The best average density for the species of fish that will go into the tank is 16 fish per 100 gallons of water. This provides enough room for the fish to swim while making sure there are plenty of fish for the people to see. The aquarium has 275 fish available to put in the tank. Is this the right number of fish for the tank? Okay, so the very first thing we're going to have to do is figure out the volume of that tank. Okay, and it's a cylinder. So I'm drawing a cylinder, which I will switch over to in just 1 second. And if you look at these two, where's my arrow? There we go. If you look at this space right here plus this space right here, the whole big cylinder, let's ignore the hole for a second. The whole big cylinder has a radius. This is 2 feet, and then this is 3 feet, has a radius of 5 feet. Okay, so we've got a cylinder with a radius of 5 feet, and I believe the height was 4 feet. Let's just double check that. Yes. Height is 4 feet. So the volume is area of the base times the height. So area of the base here is 25 pi. The height is 4. So my volume of the whole big cylinder would be 100 pi if there was not a hole in the middle. But there is a hole in the middle. Okay? So what we're going to do with a hole, it's kind of like what we did with compound figures, except we're not adding figures together. We're going to take it out. Okay? It's like we have to carve this hole out of the middle. It's kind of like a roll of toilet paper. I did not draw it very well. Okay, that hole that we're carving out of the middle has a radius of 2. Still has the same height. So what we're going to do is we're going to take this 100 pi and we're going to subtract the volume of that pink cylinder, the one I just drew in the middle. It has a radius of 2 and a height of 4 still, so pi times 2 squared times 4. 2 squared is 4, so this is 4 times 4, so this is what we get. And when I subtract 100 minus 16, I get 84 pi. So that's the volume of the tank. Now, the interesting thing about this problem, and why I wanted to do it, is they don't give me the density in terms of volume. They give it to me in terms of gallons. So I'm going to have to use good old Google to figure out how many gallons of water fit in how much volume. Okay? So I'm probably just going to go something like volume of a gallon of water in, hey, we're in cubic feet, so that's good. Let's go with cubic feet. 0.134 cubic feet. 1 gallon is 0.134 cubic feet. I'm going to write that down. Okay, so let me come over here. So if this is how many cubic feet I have, I need to know, and we can set up a proportion as one way to do this. I can say if 1 gallon is 0.134 cubic feet, then how many gallons is in 84 pi cubic feet? And the nice thing about setting up a proportion is it kind of tells me what to do. I'm going to cross multiply. So I'm going to multiply 84 pi times 1. That's still going to be just 84 pi. And then I'm going to divide that by 0.134. 84 pi divided by 0.134. That's 1969.35 or 19.69.4. Let's go with that. So 1969.4 gallons is what I've got. In this space, that's how many gallons that space will hold. Okay? So now I'm going back to the problem. Wrong place. There we go. Somehow I'm on Edpuzzle. There it is. Okay. And I need 16 fish per 100 gallons. Okay. So I'm going to do another proportion. If I need 16 fish in 100 gallons, then how many fish do I need in this many gallons? So again, I'm going to cross multiply 1969.4 times 16 gives me this equals, cross multiplying the other way, that gives me 100 times, let's call that x. Then I divide both sides by 100. That's going to give me 315.1. So this is how many fish I need in that amount of water. Okay? Or is it? It's how many fish basically Best average density for the feces. This provides enough room. So this is my ideal, is 16 fish per 100 gallons. It's not like the max or anything. So according to that, my ideal for this particular tank would be 315 fish. So it says the aquarium has 275 fish available. Is this the right number? No. We need 315 fish. If not, how many should be removed? We should add another 40 fish. Because right now, it's not going to have enough fish for, it said what? Plenty for people to see. So we want the number to be small enough that the fish have room to swim, but big enough that there are plenty of fish for people to see. Right now, my number is too small. 275 is lower than the ideal. So therefore, people would be like, oh, there aren't that many fish in this tank. I hope this is just giving you an idea of how varied density problems can be. And that a lot of times it's about figuring out what the available space is, and sometimes you have to convert units. But you're looking at how much of something is in how much space. That's basically the big idea. And every density problem is a little bit different, but you can always fall back on these two equations and see if either one of them applies to your situation, and sometimes they will. If not, it might be something very similar, like number of cows per stall in a barn or something like that. It's basically how much of something in how much space is the big idea. So hopefully that will help you to do these problems, which is where you're going from here. Notice the very first one's a population problem. Second one is an area problem. So first one, you're going to be looking at this. Second one, more like just area. It's people per area or mules per area.